Hey, that's a little bit better. You kind of see somewhat more of the blackboard. Yeah. Still not great. Hey, Joe. What?
I'm deciding whether this is okay or not, whether the track will fit nicely or not.
What, right here?
Yeah.
There should be a place to put
Yeah.
it in there.
Well, no, it's more that normally this is shifted over here.
Yeah, I know.
So-
I moved it because the cameras over there don't see the blackboard really well. So,
Okay.
and I keep having people who are like attended.
Okay.
Keep wanting recordings of lecture.
All right.
So I'm recording there.
Okay, I may need to shift some because otherwise the track won't fit,
Ah, okay.
but we'll see.
I'm gonna put my chalk. Seem to be missing my chalk.
Technical strap.
How much time do I have? I have 8 minutes.
Which one?
What? Just realized I forgot my chalk.
Hey.
What?
Great, huh?
Yeah. I can go get it probably. But I'll wait. You guys have another minute. I'll look at my chalk. I forgot. I don't see it. I'm gonna go get my chalk.
So I could just do one giant skateboard run.
Beautiful. Beautiful. Turn off. That's perfect. What do you need? Yeah.
Looks like it even, look at that. I think you even got a recording of the demo today.
See it here. Right. Length of wire.
Okay. Make it sense.
Yep. Okay, so Al, please be careful.
What?
The fact that there's a wire running through the middle of where you're getting to walk. Yes, you can.
I would need to. And you
I know.
Yeah.
21 grams says.
Yeah, you don't have to feel it. Yeah. People like.
All right. Al,
Okay, so. You have to just press start.
Yep, press start. Then go over there,
Turn on the-
turn on the air. You'd like to do it? Okay.
That goes back.
Huh?
They don't sell.
Yep, oh, that's good. And then you put a line to it. And you got a slope of 32. And so we had 21 grams. The acceleration is going to be 2.0, right? Other one. Oh, and the mass is, I need to do the mass. Okay, so we can put another weight on, right? We'll put 5 grams. Okay.
Oh, that's good. That's
Point 2.6. And that's good. I think we're set.
All right.
We basically did. the
And you
demonstration.
you certainly can continue doing it again and
Yeah,
again.
we could do it more. Yeah, we're all set. Hey, so I know you guys were kind of chatting here, but while you were chatting, I was actually doing the demonstration. So, let me tell you about what it is. So this particular thing, we have a mass of a cart, which is let's see if I can actually show. I'm working on the recordings. So this cart, it's 750 grams, which are there. And then there's this nice track. And the track, like our carts in the lab or a 7, they're minimized to reduce resistance or so that it moves without friction. Only in this case, there are these little holes in it. And so when you turn on back. Right now it's not removing the restriction on it, but if I turn on the gas, then it will start to move because there's the string here and there's tension in the string and it goes through these pulleys and then there's a weight on the end. And so the situation we have is some mass which is called one here. So let's call it little m. Yeah. Then we have a pulley here, and then it's connected to this other mass here, which is 750 grams. And then the idea is once you turn on the air, there's very little friction, and this thing is feeling mg. The gravity on this one is balanced by the table. So you don't have any gravity, but there's a tension on this string, and so the tension is equal and opposite in this direction. And so the acceleration, so ma on this thing is the force from gravity, mg, minus the tension. The tension is pulling up, and the tension should equal ma because the accelerations are same. And so you can write this as mg minus big M a because the tension has to be equal and opposite. So let's rewrite this equation. Ma equals mg. So G is known, M is known, little m is known, and big M is known. So I can solve for A in terms of these other quantities. So we move these onto the other side of the equation. And we can solve for A equal to G and so it depends on the ratio of the sum of these two. So the m's, so when I made this table here, we actually measured those two. You can see on the screen, we did it in the same way that you guys were measuring with the motion sensor. But in this case, there's a picket fence, and the picket fence has these black pieces of tape, and then there's a photo sensor that's blocked when the black pieces of tape pass by. It measures the tiny differences between those, and that gives you velocity. And so what's plotted there is velocity for each bit of tape that's blocking the light in the photodiode. And then you fit the slope to it, and that gives you the acceleration. And so we measured the acceleration A here. And so then we can see, does this equation work? Well, so little m is much, much smaller than big M. And so it's easy just to do this. That. And so we can look and say, how different are these? So 750 is kind of like 1,000. I'm really going to approximate here, but it's about the difference is about 5 grams over 3. So this is about 25%. And then if I look at the accelerations, is that about right? I think it looks actually it's bigger than that. The difference. 5, the difference is 5 divided by 1,000. That's correct, it's a 0.5%. And that's a little bit big. Because that looks like the difference is 5 divided by 0.055. No, maybe it's about right. But in any case, that's what you're supposed to get. This is there's something wrong with this arithmetic. So sometimes the you do get differences because of friction and the pulleys and stuff. Not gonna spend too much time arguing them. Okay, so that's the demonstration. So now let's go to class. So does anybody have any questions right now before we start up on momentum and circular motion and stuff? Yeah. Yeah, so tension, there's tension along the string, but it's equal and opposite because the string can't change in length or anything. And so if I pull it on this side, I pull on that side. Yeah, so they're the same. Yeah. So the tension on this side is equal to the tension on that side. Yeah. And it has to be equal and opposite along it. So strings, we'll see that later on with in lots of settings where we're using things that don't change in length. If you pull on them, then it has to pull exactly the same amount on the opposite side because it can't change in length. So the force is just transmitted through the whole thing. Yeah. Any other questions on? Okay, so last time we were talking about last time we were talking about circular motion. So let's review that a little bit. There's way too many things. Let's drop that. So let's review that a little bit. So we have, let's talk about uniform circular motion. Uniform meaning the radius is not changing and the velocity is the same. It's constant, and equivalently, the angular rotation rate is constant. So we can put a coordinate system for our uniform circular motion. And then we talked about this vector r, which goes to the location of the object that's in the circle, define this angle theta. And then we talked about the angular rotation rate like this. And if we have uniform circular motion, then this is constant. And the position r is r cosine theta. So I wrote this, you can write this as a vector. Sine theta, that's x and that's y. I can also write this as r hat, where we talked about a unit vector, which has length 1, that's pointing along the direction to the origin. I can also write this r cosine theta x hat plus r sine theta r hat, where I take unit vectors in the x direction and the y direction. It's also a squared vector, yeah. So supposing theta is increasing at a constant rate, so that means theta dot is omega constant, which is right here. But let's integrate that. We get theta equals omega t plus a constant. So I could start. So if I start theta at t equals 0, if I start theta equals 0, I can set that constant to be 0 if I want to. So let's do that. We'll just assume initial condition. We'll assume that theta equals 0 at t equals 0. And then we can get rid of that constant. So let's look at what x and y now look like. So I can just plug in here. X is t, r cosine omega t, y is t, sine omega t. That. So before we computed the velocity by taking time derivatives of x hat, of r hat and theta hat. But we could just take the time derivative of this directly to get the velocity. So d is dr dt. But I can take the derivatives of those directly. So dx is just dx dt. And r is a constant if it's uniform in circular motion, and omega is a constant, so it's sine cosine goes to minus 10, the minus sign, and theta omega is in there. Then I take the derivative. So let's rewrite that. Here, r omega sine. And so you can see there's this velocity in here. So last time we talked about the tangential velocity component, which is the velocity component in this direction, in the theta hat direction, and it's equal to r omega. Right? So for v tangential, or v theta, is r omega, which we wrote as r theta dot for. They're the same if you have uniform circular motion. So think about the units is the distance, and this has units of more over time. And so the distance divided by time, so it's in the units of speed. So that's good. So I can do the same thing for dy. You take the derivative of this. And so sine goes to cosine, and then multiply by that thing. So right, sine goes to cosine. So but we look at dx is sine omega t, there's a minus sign here, and dy is cosine omega t. So before we had theta hat with the minus sign theta, that was this unit vector that we constructed. We constructed it so that it was perpendicular to r hat. And you can see that b, we have this minus sign omega t is theta, and cosine omega t is cosine theta, that's cosine theta, so we have minus sine theta. You can see that the velocity is in the direction of theta hat, the tangential velocity. So that's consistent with what we found last time, but we're just checking it now using Cartesian coordinates. So, so now that I have the velocity vector, I can again take the derivative of it to get the acceleration. So let's take the time derivative of this thing. So sine goes to cosine r omega squared cosine omega t. There's a minus sign there. This is the minus sign here. And the y component of the acceleration. Cosine goes to sine, and then this time movement and sine. And so the acceleration is side r omega squared. And we could write this theta squared equal to r. They're equivalent. This means theta is equal to this. And the direction of the acceleration is in the opposite direction than this, the r vector. So we have cosine omega t here, cosine omega t, sine omega t, sine omega t. So the direction of the acceleration is that way, so it's radially. And that means the force you need to keep this particle in a circular orbit is radial and towards the origin. And so when I gave that demonstration where you have the little ball going around the circle, I'm just holding it by the string, the tension of the string pulls it towards the center. But the same thing's true for orbits. Yeah, like the Earth going around the sun, or the moon going around the Earth, or a satellite going around the Earth. The direction of gravity is towards the center of the massive body. And so that means the thing can stay in the orbit, because the acceleration is such that the particle is curving, there's a curve, nearly circular. And all of these settings, the orbit's nearly circular. Yeah? Oh, yeah. So remember the length of the vector? Like that, but cosine squared plus sine squared is 1. So I just did that automatically, but I could have made it clear. So if I take this squared, cosine squared, this squared, sine squared, the cosine squared plus sine squared would give me 1, and I take the third and get that. Yes, good question. Yes? Oh, yeah, I managed to switch notations here. That's what I meant. They're both omegas. One of them's a capital omega, the other one's a small omega. Sorry about that. I didn't even notice. Like, oh, that's great. Okay. Okay, so that's, oh wait, yeah, there's one last thing I want to do with circular motion, and that's plot things. The uniform circular. While we're continuing on the uniform circular motion, let's plot some variables. So if we plot theta as a function of time, so we found that theta is equal to omega t. And so theta is a function of time, which is like this. So the angle theta just keeps increasing forever, and it goes from 0 to 2 pi. This. And the slope is omega. So theta just advances forever. It's a little bit different than a pendulum. If you have a pendulum, then theta kind of goes back and forth around 0. Here, theta is increasing forever. So what other variables can we plot? We could plot x and y as a function of time. So I just erased the right, but so I have x. So x, so remember x was r cosine of t. So x is starting with whatever r is, and then does the cosine, and then it just repeats. Then y is sine omega t, and so y starts with 0 and that, and it's delayed with respect to x. So when we reach this point, y is in. So they're both sine waves. One of them is delayed with respect to the other one. Yeah. Yeah. So that kind of, just get used to plotting. What are these different functions like? Yeah. Okay, so that's circular motion. So we've been kind of, in this setting, I talked about forces, kind of jumped ahead. Now we're going to be a little bit more, just going to think about what we mean by force. So anybody remember what Newton's laws are? Yeah, we have somebody who knows Newton's. Okay. Yeah, so wait, something stays in motion. The natural thing things stay in motion. Sum of all forces should be 0, I think. What was what else? Yeah, Abby? Right. Okay, so those are Newton's laws. So we're gonna be a little bit more general than that. So the idea that something that has a constant velocity, if there's no force on it, that it will stay on that trajectory, straight trajectory, that's still good. The some of the equal and opposite force thing, we're gonna keep, but the thing that we're gonna change is F equals ma, and the reason for that is that only works for low velocities. So it with modern physics, you have this issue that the speed of light should be constant in all velocity frames. And so we're gonna adopt fundamental principles that are consistent with special relativity without going into much detail about special relativity, which is that's kind of annoying in some sense. So first let's just look at momentum. So momentum changes in force. So so let's momentum changing force. So mainly so if you have a force, So we're gonna be more specific about what momentum is in a second, but you have a force and you apply it for a time delta t, then you get a change in momentum that looks like this. So if we have a time interval delta t, and we have a force F, then you get a change in momentum. And force can be applied as a vector. So this is a vector and that is a vector. So your change in momentum is also a vector. So I can take this delta t and divide it, divide both sides by both. But force is delta t over delta t. And if we shrink our time intervals, we can write this as I don't need the dot because I took the derivative, or you could write it as p dot. So force is defined as a change in momentum. And this is true in Newton's laws too. So with Newton's law, and momentum is mv. And so if I take the time derivative of p, then well, this is a is dt, and then I can move this m inside here. So this momentum principle, which is this, so this is the momentum principle. Yes, I'm spelling right. Is consistent with what we know as Newton's law. But it's actually a little bit more general because we're going to redefine momentum to be consistent with special relativity. So, right. So this is what we can call the non-relativistic limit. So what do I mean by the non-relativistic limit? What we mean is that the velocity is much less than c, where the c is the speed of light. So as long as you're working in the lab and all the velocities you're dealing with are low, meaning much less than the speed of light, then you can use Newton's laws. And in that case, F equals ma, and momentum is equal to mv. But if you're in the relativistic limit, you want to, use this, and then you want to use a different definition for momentum. Okay, so what are we going to use for our new definition of momentum? So if you keep speeding up a particle and it can't get faster than the speed of light, then and I keep here's the non-relativistic setting. We want to change this definition. So V can't get any faster than C. And if I kept the mass as a fixed object, like an intrinsic property of something, then that would give me a limit on momentum. So if you want to be able to have momentum get arbitrarily large, then one possibility is to change your definition of mass. The other possibility is to change your definition of momentum. So you can let it get big, and even if the particle gets close to the speed of light. So there's trade-off. So if you're a theoretical physicist, you could say, well, why don't we just change our definition of mass? And I think that makes the theory much worse and much uglier. So you get nice symmetries and better predictions. And so physicists have adopted the second approach, which is to change your definition of momentum. And so for fast particles, so V, so I'm using notation. So V less than C implies that V is much less than C. This means that V is of order C, can't get faster than C because Nothing can go faster than the speed of light. So for this, then you make the definition of momentum look like this. So, it's still a vector. Only now we have this new thing called gamma. Gamma is the length factor. What it's called. And what it looks like is this. And you can also write it. Sometimes you can write it that with data. So this is a definition. Sort of the expression. Probably defined with. So this is the length of V. You can write it like that. This is the length of V in here. So what happens as V goes to 0? V goes to 0, or actually I really want to do V over C goes to 0. So since beta is 0 over C, let's take the limit of beta goes to 0. So that's the same thing as saying the velocity is small compared to the speed of light of gamma. Well, it's pretty easy to evaluate because it's just like beta goes to 0. Then you get so the limit is equal to 1, right? So in the limit of velocity, in the non-relativistic limit, which is the same thing as saying velocity is small compared to c, so limit being 0 to c, we're going to use this definition. So lambda is now going to 1. So the non-relativistic limit of this equation is equivalent to our what we expect if Newton's laws was correct. So Newton's laws are perfectly accurate for low velocities. So this generalization, this relativistic generalization of our definition for momentum is consistent with Newton's laws in the non-relativistic limit. It's kind of a mouthful, right? But you get the idea here. So it's like we're making a more complicated theory that takes into account special relativity, but it's consistent with all the physics we knew beforehand with Newton's laws, just in this limit. So it's kind of like general relativity is consistent with Newtonian gravity, as long as you don't have really heavy things like black holes, and special relativity is consistent with Newton's laws if you're not moving very fast. So these are one approach to making better theories, is you make it consistent with what you already know, but that they also have different phenomena associated with them. Okay, so right. So what happens to gamma as the velocity gets big? So as the velocity can get bigger than the speed of light, but as this approaches 1, this denominator gets really small, and 1 over something really small gets big. So, so the limit of E goes to gamma is infinity. So gamma can get arbitrarily large, and that means your momentum can get arbitrarily large. So if you have particles that approach the speed of light, they can have a lot of momentum with them. That's true like for accelerators, right? They accelerate particles going nearly the speed of light. They have lots of momentum, which means when they hit something, there's like a lot of energy in the impact. And that's how particle accelerators, reach really high energies. Okay, so last thing, what's M now? So M gets this fancy name now. It's called the rest mass. So this thing here. Okay, so we got the momentum principle. So most of the stuff we do in this class is gonna be using Newton's laws, but every once in a while we'll throw in like calculated gamma so that you get a little bit of the modern physics. So the principles now. Where are they? Of relativity and momentum. So, the first one is that if you're in flat space time and there are no forces on a particle, and a particle drifts at a constant velocity. And then this is if there are no forces on it. And we have flat space time. So that caveat just comes from general relativity, because general relativity, you get curved trajectories. Then the second one is laws of physics should be independent of the velocity of the observer. So sometimes people call that reference frame. So when you start to learn about special relativity, which you should either maybe in your E&M class, I'm not actually sure where you learn special relativity, but when you actually go through things like Lorentz transformations, those are ways to transfer from an observer that's moving with one velocity to an observer moving with another velocity. The laws of physics should be the same. They shouldn't depend how fast you're moving, as long as you're not accelerating. So if you're accelerating, then you get things that look like gravity. But this is where the relativity comes from, and it's the basic assumption that gives you. If you use that assumption and try and make the laws of physics independent of an observer's velocity, you would derive that form for the momentum, and the Lorentz factor comes out of the transformation, which is called Lorentz transformation. And then the last one is our momentum principle, which is that forces cause changes in momentum. That's the last. So that's F equals D. F is equal to and in the non-relativistic limit, that's equivalent to F equals MA. So those are our principles for what we're doing in this class. And those are they're kind of fundamental. Okay, I'm going to skip this right now. The next topic is how you predict positions in forces. So we'll do that. So let's talk about gravity. Okay, so let's talk about the gravitational force. So let's take two particles. We have F1 and M2, those are the masses. That's their masses. So we have M2. And the positions would be what are called X or R. They're called X. Those are the vectors. So you can pick an origin at some place and then x1 goes from the origin to that position, and x2 is from the vector from the origin to point 2. So there's a vector between these two particles. And this is R, so I called it 1, 2, 1. 2 minus 6. So the vector between them are 1. So if I'm at the position of x1, I want to know what direction to go to see R2. That vector tells me what the direction is. So I can also define a unit vector along that direction, and vice versa. If I'm at M2 and I want to know what direction x1 is, I just take the opposite sign of this vector. So the force is exerted in the direction between them. So, you know, M2 is feeling a force, attractive force towards M1, and M1 is feeling attractive force towards M2. And that force is in that direction. And that's why this vector is important. So sometimes it's helpful to define a unit vector, which we can write in various ways. Or I could also define power 1, 2, 1. So I can write this. It doesn't really matter once you're doing a length, but so this is the length of this vector, right? So remember lengths, yeah? Question? Oh, yeah, I meant them. It doesn't really matter where the origin is on this plot, because the only vector that I'm really worried about is the one between them. So it doesn't matter where it is, you can draw it in. The important thing is this direction between the two, because the force on one is towards the other one, right? So the force is equal to G M1 M2 divided by R squared in the direction. So this is the gravitational force from N2 onto M1. You just have to get the sign right so that it's attractive. So this is a constant known as a gravitational constant, and those are masses, and then the distance for them. So force here, force is a mass dependent acceleration, and so that is enough information to get you the units of G. So, and I think the units of G are on the web work, right? People who've done the web work, you guys know the you guys know the units of G. You can figure out the units of G if you want to. So, but this whole thing, like, why did I write it like this? I just wrote it like this. It's clear that it's in this direction along the two particles, right? And then the size of it depends on the masses. So, if you have a really big mass, then you have a big force. If you have a really small distance, you have a really big force. So the distance between them makes the force go bigger. If they get closer together, you have a bigger gravitational force. And likewise, so this was a force from M2 onto M1. If I want the opposite way, I just flip the sign because this changes the opposite sign. So let's write down what the gravitational constant is. It's about 11, and MPS is 100 kilograms. I always remember it like this. For meters. 3 seconds. Oh, what's N? Yeah, so N is a Newton, which is a MKS unit. Oh, and there should be a square here. So we can check this because this is a force. So if I multiply it by two masses, I get rid of this. And I divide by one distance, that's distance squared. I get rid of that and then just reduce. So. Okay, so yeah, so this is enough now to do an n-body, think about n-body systems. So in like planetary settings or galactic settings, you can think of so planet to one planet feels the mass from the sun, the attractive force to the sun. It doesn't fall into the sun because it's on a circular orbit, nearly circular orbit, right? So that, just think about that thing going around in the loop. The radial force keeps it so it doesn't fly away or doesn't hit the sun, even though it's an attractive force. Then that planet could also feel the forces from all the other planets. And so in general, if you have an n-body system, the force on one mass, this big N, you would sum over all the attractive forces from all the other particles. And so I can write that out. So I'm using the index I to index all the other particles in the system. And then I have to have this R thing, the distances through all the other particles squared. And then I have to have a unit vector that points to the other particles. So this is 25 M. So I could put a hat on this, or I could just do it. And then one of these will normalize that. So you'll see it. In this case, if I multiply both sides by R21, I can store the vector, and then I have R2 over here. So that's what you do in an n-body system. You take every particle, you add all the forces up from all the other particles, and you say, okay, which direction am I going to move? Because it's velocity. And then how do I change that velocity? Because a force changes velocity. So you change its velocity. And then you do that with all the particles. And then you do another step where you like add up all the forces again, compute the accelerations on every particle, and then compute what their velocities are and what their new positions are. Yeah, question? Yeah, so I could do this. Let's write it. So in order to make this discussion, okay. So this is now the unit vector pointing between particle I and particle M. Putting the force on particle M. If this is the same as that, so I can move that. That's what I did. So you'll see it look like this often. Because it's a lot easier to do the vector. Yeah, it's the same. More questions? So that's what an n-body. Yeah. And n-body simulations are like this big industry nowadays. So people do it in planetary settings, people do it in galactic settings. You'll see beautiful n-body simulations of galaxies. They have billions of particles, literally. And billions of particles is quite an effort to sum up all the forces. So yeah, so in one thing to look at with the force, it goes as 1 over r squared. So that's considered it never really goes to 0. So if you have electromagnetic forces, charges, so gravity, you always have attraction, you don't have any repulsion. With electric charges, you have plus and minus forces, because you can have positive charges and negative charges. With the mass is like a charge here, but they're always positive. With electricity, often, most the universe adds up to having 0 charge. And what that means is electric forces tend to decay. They don't persist over long distances because they cancel out after a while. Gravity never goes away. And so even though gravity is a relatively weak force compared to electromagnetic forces, so, molecules combine together to make things like solids and air molecules, electric forces are stronger, but over long distances, gravity wins. so that's why when you're thinking about galaxies or you're thinking about planetary systems, then gravity is the only force you worry about. So you can think of gravity as a long range force. So this 1 over r squared part of gravity and the fact that it's always positive, always attractive, means that it's important on large distances. It's a long range force that you can never ignore it. It's always important. Okay, so yeah, so let's talk about the shelter. Shelter. So the setting for the shelter, you have this, not a ring, it's a spherical shell. So this is, got some thickness. Spherical shell. Uniform thickness. Uniform density. That's the setting. And it's a sphere, right? So, then, what the shell theorem says is, there's no gravitational force in the inside the shell. So it makes sense that there's no force in the center, because this, this bit would cancel out this bit, the gravity force is this way, from this little bit of mass, the gravity force is that way, it would cancel. But it's not obvious that if I take some other point, that these particles are nearby, these little mass particles are nearby, so they have more gravitational force, but there's more of them on this side that are further away, but they cancel out. And so there's no gravitational force inside the shell. So we could show this with a really nasty integral. Yeah, question. Thickness, uniform thickness. Sorry, my handwriting is not straight. Uniform thickness, uniform density shell. Okay. The force is 0 inside the shell, and it's not obvious that that's true. So the 1 over r squared force law, you can prove that it's true, and you can do the integral directly. So how would you do that? You do an integral over all solid angles, and you compute the force for each little tiny bit of solid angle at a position inside, and it would be a kind of a painful integral to do. But why are we not doing it? And that's because you can prove it in one line. Once you prove Gauss's theorem, which is part of multivariable calculus. So when you take multivariable calculus, one of the first theorems you're going to learn is Gauss's theorem, and then you can prove this essentially with one line. So we're going to wait for you guys to take multivariable calculus, and then we don't have to do the integral. So, and that Gauss's law is useful in electricity and magnetism because the force has the same behavior. It goes as 1 over r squared. So you can also prove it. It also works for charge distributions too. So that's one bit. If you're outside, then the force isn't 0. So outside, the force is, so you take the shell, you figure out what the mass is. So it's equivalent to a mass that has the same mass as the shell. Equal to that of the shell. And you put it at the origin or at the center of the shell. So this, if I'm out here, the force from the shell is equivalent to the mass of the whole shell, just like the center of it. And again, this is a one-line thing to prove with Gauss's law once you've taken multivariable calculus. So this makes things a lot easier to calculate things. So like you have a planet, you can give a planet as a bunch of different shells. And inside the planet, you won't feel the force from the outer shells because you're inside it, but you'll feel the force from everything inside. So if I think of a planet with a series of shells, approximately, that doesn't look right, but like if I'm in the center, then you're inside all the shells, so there's no force on you. And if you get out here, you're inside most of the shells, you can still feel the force from everything below you. And if you're out here, you feel the force from everything below you. You integrate up the mass up to that radius, and you'll feel that. You'll feel the force from that. So this is dependent upon being a sphere. So if I take a ring, oh, this looks like a shell with this little ring. The shell theorem doesn't work for a ring. So I mean, you're here inside a ring, like say you're on you're somewhere in Saturn's rings, you will feel the force from a little bit of a force outward because it doesn't all cancel out. So you need it to be actually a sphere, not a ring, in order for the shell theorem to work. Yeah?
I'm not sure if I understood that correctly, but like, so you said outside, there would be a point in which that an object would exert a force of like equal to basically zero.
So
like it's equal to what's inside the center of the sun. You have a gradient of zero.
yeah, but if I have a planet, you can think of a planet as a series of shells. And then the force from, if you're inside one of the shells, you don't feel the force from it. You'll feel all the force from everything below you. Okay, so the shell theorem just says inside there's no force, outside it's as if the mass are all in the center. But if I'm on a planet, you can think of a planet with a whole bunch of shells. And then you just add, if I take a particular radius, you feel the force from all the shells inside you, but not any of them outside. That's the point. Yeah. So, but you could do more. So with a ring, it doesn't work. It's 2D. You need it to be a 3D shell. And that means that forces of, like if you're in a ring system, you do feel forces inside and outside that are different than predicted by the shell theorem. Yeah, question? Oh, you're inside the shell. Yeah, so if the shell's not infinitely small thickness, you could just divide it up into little shells, right? And then you just decide how much mass is inside, how much mass is outside, where you happen to be. Yeah, you would feel some. So if you're halfway through, you just divide it into 2 shells. One is inside, one's outside. Yeah. Yeah? In what? Yeah, yes. The same theorem works for electricity because the force is also 1/r² force law. Yes. And the theorem, Gauss's theorem, works in both settings. You have a different coefficient. Instead of G, you use charges. And instead of mass you use the electric charge, which just depends on, yeah, so the constants are different, but the theorem also works. Yes. That is exactly right. So, yeah, so let's do something a little bit more challenging that might be relevant to your problem set. So, supposing I have a sphere, and it's a uniform density sphere, and I was pointing out to them. I know it's pretty easy to figure out what the force is. I just need to figure out this distance. And I need to know the mass of the whole sphere. And so the force would, so this is little m, and this is big M, this is R, and R is this distance. Okay. So now supposing I add another sphere inside this guy. So that's equivalent to saying I'm adding in a higher density somewhere in the middle. But it's also a sphere. So all I need to know is the extra mass that's in this, as long as that's a sphere, I can add it on. And then but I need this distance. And I need to know the mass of that. So, but I could also say, what if I lower the density in that region? Then, you know, that's as if I'm subtracting off a force that I estimate in the same way. And so this is essentially what that problem where it was hollow. You just have to think about, well, I know the force that would be from the hollow filled in because it's a sphere. And I know the force from the whole thing filled in. And then you just have to figure out how do I, from that, calculate the force from the sphere with the hollow missing. Yeah.
What does that say G and R?
Oh, yeah, it should be G and over. Now, after that, G and over. It depends on the distance squared and it depends on the product of the measure. So with this, now I need to have a, if I have an extra density, increased mass, I'm gonna have to figure out this distance, so let's call it D. And then I have another mass, let's call it one prime. I would add G and prime. And that would be the force on sign off and practice. So you need to figure out the distance to the center of this. Yeah. Right, if it's lower density, then you would actually subtract it. Because you want to, but you could think about it as if, you know, the mass is if it were even, and you would, you know, I mean, you could put, you know, you could say, so supposing it's lower density, and I figure out what amount do I need to fill it in to get this. And then you subtract it off the other side. So, which is equivalent to just saying, yeah, I'll just throw in a negative mass. People are uncomfortable when you think about negative masses, but in terms of arithmetic, it's the same. you can treat it that way. Yeah. You just have to. Yeah. So you want if you have one density here, one density here, so keep the difference.
Yeah.
Yeah, because you want to add it on. Yeah. Yeah, that's exactly it. So you've got the idea of how you use the shell theorem. Basically, just reduce your problem to a bunch of spheres or a bunch of shells, and then you don't have to do any integration. Otherwise, it's a lot of work to integrate of the mass distributions. Okay, so that's the shell theorem. Oh yeah, so let's do let's get big G from little g. Doing good. Okay, so let's relate big G to big G is the gravitational constant in the force law that we just gave. Little g is the gravitational acceleration downward when you're on the surface of the Earth, right? So our force, so we have our planet, in this case is the Earth, right? It has mass m and it has radius. Here it has radius. So if I'm a person sitting on the surface, the force from gravity is in the radial direction downwards. So minus g, and we'll give this guy a little mass m over r squared times r hat, where r hat is downwards. Right? So the acceleration, just divide by m, because f equals ma, and then off relativistic limit. acceleration looks like this. So now, R is really big, right? The Earth is pretty big. So when you're locally, some guys are locally sitting, guys in there, R is down. And so if I make a coordinate system with Z locally up like this, then R hat is equal to Z hat. And there's not a lot of difference because the radius is so big, right? And so you can approximate Z hat, you can approximate R hat, where R hat is towards the center of the Earth, and Z hat is the local coordinate system from the local coordinate system pointing upward. And so that means the acceleration from gravity, so let's make it clear that gravitational acceleration and minus T. So for us we define that as G. So G put in the mass of the Earth and the radius of the Earth. So that's how you so if you know the radius of the Earth and you know little g, you can figure out what big G is if you use this. So there's a constraint between the mass of the Earth, the radius of the Earth, and the gravitational constant. Yeah, but then this is now general enough. You could say, what's the gravitational acceleration on the moon, for example? And since you don't necessarily need to know G in order to write it in terms of the ratio of the Earth, the Earth's gravitational field. And so I think with the moon, the gravitation G is about 1/10 of the Earth, maybe, and that the mass of the moon is like 100, but the radius isn't quite 100. The radius is maybe 1/10. So it depends how the factors cancel out. But you can, knowing radius and mass, actually, one thing that's in general true most planetary systems is the densities are not that different. So mass goes with density radius cubed. This is radius squared. And so to order of magnitude, this is like 4 pi rho r for a body, and densities don't vary that much. And so to order of magnitude, G goes up. So if you want to estimate something really quickly, you could just say, oh yeah, the Earth has a radius of like 6,000 kilometers or something. You look at an asteroid 100 meters and you figure, just take the radius and increase the gravity acceleration on body. Because densities aren't that different. There's a little bit of a difference, but not a lot. Okay, so that was G and G, the different units. They're not the same units, though. So this is an acceleration that has mass and kilograms and meters and seconds in. Yeah. Oh, I just was arguing the gravitational acceleration on Earth, we usually give it a Z direction. We usually choose a coordinate system so that Z is up. And so gravitational acceleration for things like, dropping this thing, this thing, we put it in the vertical direction and it's based on little g, which is an acceleration, but it's not inconsistent with this gravitational force law that looks like that on Earth. And so you can calculate little g from the mass and radius of the Earth if you use the gravitational constant, which is that. So this is the fundamental constant for a force. That just happens to be the acceleration on Earth. It's not a fundamental number, right? It actually varies a little bit too. I mean, it's not the same everywhere. It's a little bit less on mountaintops. Okay. We have a little bit more time. So, so Newton's third law, is that you have equal and opposite forces. So our gravitational force, equal forces have equal and opposite, equal and opposite. So looking at our gravitational force law, that was definitely true, right? So if I have P1 is equal to G M1 2 over R where so actually let's do it in this form. That these are all different. And then F1, 2, this stays the same, but that flips sign, right? So our gravitational force gave F1 and F2. And these are vectors. And so that means, you know, they're equal and opposite. So remember from the momentum principle, the force is a change in momentum. So, so this implies that P1 is equal to minus P2. And so I can move those to the opposite side. P1 of P2 is equal to 0. So I move this to this side, and then I took the time derivative out, and these are all vectors. And this means that P1 from P2 so I've integrated, and if the time derivative is 0, that means the sum is constant. So the total momentum is constant. When we call that conserved, so there's a conservation law. So if I have n particles and they're all interacting gravitationally, every force has equal and opposite force. Force law is symmetrical. I can sum up all the momentums, and all of, because they're equal and opposite, every pair will cancel out. And that means the total momentum for the system will be conserved. So you can already see that the momentum principle gives us a conservation law. Momentum is conserved for n-body systems. Okay. Yeah, so let's talk about Kepler's laws for the moment. Yeah, so this is fine. Oh, you're like, it's just enough time to squeeze in. So, so let's take this setting where we have a mass and then we have an object, little m. So we'll assume this is really, really big. So think the Earth moving around the sun. And we'll put this, so which direction is the force? The force from gravity is towards the sky. Because this guy is so big, it barely isn't really buzzed by the other. So the sun is really, really massive. It's like 1,000,000 times more massive than the Earth. So the sun doesn't really feel the Earth much. So it basically still. So, so I'm going to ignore the back direction on the sun. So the force on this guy is minus G, and we'll label this R. And R squared. R hat is towards the center of the sun. So this is the gravitational force, using our gravitational force. So remember when we had a particle in a circular orbit, the acceleration is towards the origin. And so we have M, and let's write A in terms of the tangential velocity. And it's in the same direction towards the sun. So we can get rid of these two little m's and we get rid of one r. And the signs cancel. The directions are consistent. Very good. And so we get an equation for d theta squared. It's g down. And so d theta. So we have a relation for the tangential velocity for a particle in a circular orbit, meaning the Earth going around the sun or something like that, or the moon going around the Earth or satellite going around the Earth, as long as it's a circular orbit. So remember d theta is r times omega, where omega is the angular rotation rate. So we can now solve for omega. We have r, and usually you write it like this. So I'm just going to take the extra r and stick it inside the square root. So the rotation period. So this is the angular rotation rate for the orbit. So remember, omega was pretty hot. So the period of the orbit is 2 pi over omega. So that's 2 pi r. So this is inverted this. So here it's squared 2 pi squared of 2. So this tells you that the orbital period goes as the radius to the third. The orbital period squared goes as the radius cubed, and that's one of Kepler's laws. So in fact, it's the third of Kepler's laws. This is orbital period. We call it the second major axis. So we proved Kepler's third law for a circular orbit. You have to do more work to show that it's true for an elliptical orbit. So Kepler's first law is that orbits are elliptic. We will prove that when we talk about angular momentum around week 8. And Kepler's second law is problem 7 on your problem set. And Kepler's second law is that the is to drive. Kepler's second law is if I take this vector and I look at the area swept in the orbit by this vector that goes to the sun, the rate that area is swept by that segment is constant. So that's Kepler's second law. And you'll prove that that's true in, it's true for any setting where you have a radial force, and that's got to do with angular momentum conservation. And so we'll revisit that later, later on when we talk about angular momentum, but you already know enough to prove it with using the derivatives in polar coordinates. So you can work through it on the 7th problem for your problem set. So on the 7th one, when you take a look at it, the amount of work you need to do is small. You only need to write a couple lines down. The hard part is reading through it and understanding the steps that are in the problem. So when you figure out what you're supposed to do, be like, that's it. And the answer is yeah. Once you understand what's written, it's not a very, you don't have to do much calculation. Okay, so that's enough for today. And we kind of got through everything that we needed this week. Yeah, we're done. There's always. What's up? Yeah.
So,
Let me just end this.
White House. Sorry. So White House,